Welcome to IB Chemistry exam preparation, exam tips for both standard level and higher level. Today, through our lesson, we will practice on past paper questions taken from paper 2 for topic 11.1, Uncertainties and Errors in Measurements and Results. So, let's get started. We're going now to start with some past paper questions. We're going to apply on how to find the total percentage uncertainty. How can we calculate our final answer to a correct number of significant figures, besides finding the absolute uncertainty for the final answers. So let's start with our first question. Question number 1. Calculate the concentration of zinc nitrate solution which is made up of dissolving 3 gram plus minus 0.01 gram of zinc sulfate in a volume of 200 cubic centimeter. Include the percentage uncertainty and the absolute uncertainty in the final answer. Now the question here is asking me to calculate the concentration, so I need to apply on the concentration rule. But before calculating the concentration, I need to start with the mole number. So we will start with the mole of the solid, which is mass divided over the molar mass. The mass is given as a 3.00. Using the periodic table, we will find out the molar mass. We have the zinc, which is 65.38 plus we have 2 nitrogens presented, so we will open the brackets 2 times 14.01 plus we have 6 oxygens, so 6 times 16.00. Now we're going to divide 3 divided over the molar mass, which is 189.4. Here we need to remember that our final answer should be correct into the smallest number of significant figures presented. You have the mass 3 significant figures and you have the molar mass as 4 significant figures. So the final answer should be 3. So using the calculator, the final answer is 0.0158 mole number. Now after calculating the mole, I can go through the concentration rule. The concentration is equal to the mole, which would be divided over the volume. But here we need to remember that the volume should be in decimeter cube anytime we want to apply on the concentration. So I'm going to divide over 1000. And my final answer would be a 0.2. I'm going now to apply on the concentration rule. So it is 0.0158 divided over the volume, which is 0.200. Now using the calculator, another time my final answer should be correct into 3 significant figure. Using the calculator, the final answer, it will be 0.079, but I need to add a 0 in order to have 3 significant figures. And my final answer is mole over decimeter cube as concentration. So I firstly calculated the concentration, so I'm done with the first step. According to the question, it's also asking me to find out the percentage uncertainty. So now I'm going to go through the second step. In order to determine the percentage uncertainty of the concentration, so here we need to remember that we need to take the percentage uncertainty of each variable presented inside my law. So I will take the percentage of mole and I'm going to add it to the percentage of volume. Before applying, going back to the mole is taken from the percentage of mass. So I need to refer back into the mass plus the percentage of molar mass, and I will also add the percentage of the volume. So in this situation, I wrote down the whole different percentages that I need to add. The percentage of molar mass, it is considered as being constant, so it will not be included. Now I need to calculate the percentage of the mass and the percentage of the volume, then to add them together. So if we go back to the question, we're going to find that we have 0.01 gram, so plus minus 0.01 gram for the mass, and I have the volume, which is half. So I will now apply on the percentage uncertainty calculation. So I will take the absolute of the mass, which is 0.01 according to the balance reading, over the value of the mass, which is 3, and I'm going to multiply times 100%. So in this situation, I calculated the percentage uncertainty of the mass. I'm going now to add the percentage uncertainty of the volume, and it is half divided over 200 times 100%. Here, when you want to calculate the percentage by mass of volume, there is no need to convert into decimeter cube. So you can simply take it as cubic centimeter. Using the calculator, your final answer is 0.58%. So in this situation, I calculated the total percentage of my concentration. Now, the last step inside the question, it's asking me to calculate the absolute uncertainty. So I need now to find the absolute, which is the plus minus uncertainty of my final concentration value obtained after doing my calculation. So in order to find the absolute uncertainty, I'm going to take my percentage, which is 0.58. I'm going to divide over 100 since it's a percentage. Then I need to multiply by the value of the concentration. Where is my value? It is presented right here. So you will take your concentration value and you're going to multiply by this value. So it is 0.079 and a 0. Using the calculator, your final answer, it will be plus minus. The calculator will give you 0.004 and 5. Now, in order to take the correct number of decimal places for your final answer, if you look at your concentration value, you're going to find that you have 4 decimal places. So the uncertainty, it is in the inexact number, which is the last 0. So I need to have the same as 4 decimal places. So the 5 will give the 4, and your final answer, it will be plus minus 0.0005. So this is an indication that your concentration value, when you want to write it in a correct way, it will be 0.0790 plus minus the uncertainty, which is presented for this concentration, and your final unit is mole over decimeter cube, and you are done in the first question. We're going actually to apply on more and more ideas. So now we're going to start with question number 2. The Gibbs relationships is delta Gibbs equal delta H minus T delta S over 1000. This is a very important rule. You will actually take it in chapter number 5, which is the energetic chapter, as a higher level. So far, if you don't know this relationship, it's not important now, since we're going only to apply. So we are doing calculation. No matter what are these values expressed for us, it's not important now to know exactly what are these values. We have the values of the delta H, which is the enthalpy. T stands for the temperature. Delta S, it is something called by the entropy. The question is asking to calculate the value of delta Gibbs and its absolute uncertainty expressing both values together with the appropriate significant figures. So the first thing is to find out the value of the delta Gibbs. Of course, after calculating, it's also asking to find out the absolute uncertainty. You can't find the plus minus uncertainty if you didn't apply on the total percentage uncertainty firstly, since you are multiplying and you are doing an addition and subtracting. So what I'm going now to do, the first step in this situation, I'm going to find out my delta Gibbs. So I'm going now to apply on the rule. So delta Gibbs, I will take the numbers which are the delta H and the temperature, delta S, I'm going to substitute. So I have negative 770 minus the temperature, which is 373.0, multiplied by the entropy, which is 19.6, divided over the 1000. Using your calculator, you will firstly do the first step, which is negative 770. Then you're going to subtract 7.3108. If you look at your final answer, now you need to think about how many significant figure your final answer should be. So look at all the numbers given according to the law. Here I have 3, or I can say as a final answer, it's more as being 2 since the 0 is not counted. So this is a 2, this is a 4, and this is a 3. Using your calculator, your final answer should be correct into 2 significant figures. So the calculator will give you this number, negative 777. How can you rewrite this number into a correct number of 2 significant figure as your final answer? You can go through the scientific notation while writing. So this will become negative 7.8 times 10 to the power of 2. So in this situation, I wrote my final answer into a correct number of significant figures, taking the smallest number of significant figures given. After that, I need to find out the absolute uncertainty, but before I need to find firstly the percentage uncertainty of my delta Gibbs. So the percentage uncertainty of the delta Gibbs, I'm going to take the percentage of all the numbers and variables that I have. So it is the delta H uncertainty plus the percentage of delta entropy and the temperature. I will start with the temperature plus the percentage of the delta S. Now you will apply on the uncertainty for each number given. So go back to the question. You have a 20 in delta H, you have plus minus half, you have 0.7, and you have the values. So I'm going now to start with each one. I will open a bracket. My delta H, it is a 20 divided over 770 times 100%. Here, when you want to calculate the percentage uncertainty, it's not important to take the negative value. Plus, you will take the delta temperature, which is half, the absolute, which is half, divided over the value of the temperature, which is 373, and you're going to multiply it by 100%. Finally, you have for the entropy, which is 0.7 over 19.6 times 100%. If you look at my calculations, each time I'm taking the percentage, I'm taking the absolute over the value times 100%. Using your calculator, it is 6.3%. Now the last step is to find out the absolute uncertainty for my calculation. So now I have the absolute uncertainty, which is the plus minus for my answer. So I'm going to take the percentage, which is 6.3. I'm going to divide over 100. Then I'm going to multiply by the value. And the value, it is presented right here. So I'm going now to label it. When you want to multiply by the value another time, there is no need at all to take the negative. So 7.8 times 10 to the power of 2. The negative is only used as an indication of having exothermic chemical reaction. This is something related to energetic chapter. So it will not affect if you didn't take it into consideration while doing your calculation for the percentage and the absolute uncertainty. Using the calculator, your final answer would be plus minus 49 kilojoule per mole as a final answer. And you are done. Now we're going to continue with more ideas. I have question number 3. In question number 3, Michel carried out an experiment to measure a certain quantity, no matter what's the quantity that I have. The value he obtained was 56.1 plus minus half kilojoule. The literature value for this quantity is 55.2 kilojoule. The question is firstly asking to calculate the percentage error. So what is the percentage error rule and how can we apply on it? So let's start calculating the percentage error. We need to remember that the rule is percentage error equal, we will take the absolute uncertainty. We need to take the actual value. The actual value, it's the same as the literature value. So it's the actual, which is 55.2 minus the experimental value, which is 56.1 divided over the actual, which is 55.2 multiplied by 100%. The absolute value is important, so to overcome the negative, and your final answer is 1.63% and you are done. Now the second part from the question B, the student mentioned that any errors could be explained due to random uncertainties. Is he correct? Explain your answer. In order to look for what are the types of errors presented as random, systematic, or both, we need to make a small comparison between the percentage error and we need also to find out the percentage uncertainty. So now the first step is to find out the percentage uncertainty of the experimental value. In order to find the percentage uncertainty, going back to the question, I have the absolute, which is half, over the value times 100%. So it's a half divided over the value, which is 56.1, and it is multiplied times 100%. And your final answer would be 0.89%. Now I will be comparing the percentage uncertainty with my percentage error. So I will find that the percentage error taken from part A is larger than the 0.89 as a percentage uncertainty. What does this mean? This is an indication that the experiment contains both systematic and random. So we cannot say that it is only random. Systematic is so important here. According to what's mentioned by the student, the question says the student mentioned that any errors could be explained due to random uncertainty only. So this is incorrect. So what can we write? Of course, this is incorrect. So is he correct? Of course, no. As the percentage error is higher than the percentage uncertainty. So this means that we have both systematic and random. So full stop. This indicates having both systematic and random. And random errors. So it is so important if you want to decide what's the type of error presented to make a small comparison between the percentage and random errors. Now we're going to start with question number 4. A thermometer which can be used to read to a precision of plus minus half degree is used to measure a temperature increase from 30 to 50 degree. What is the percentage uncertainty in measurement of the temperature increase? So the question is asking to determine the delta T, and we need to find out the percentage uncertainty for it. So firstly, I'm going to find my delta, which is the increase in temperature. So it is T final, definitely minus T initial. So it will be 50 minus 30. And my final answer is 20 degrees. Now, in order to determine the percentage uncertainty, we need to take the absolute of the delta, and we need after that to go through the percentage. So the first step is to find what is the absolute. Since we subtract two values, so what we're going to do for the absolute uncertainty in case of subtract or addition, we're going to take the plus minus and we're going to add. So plus 0.5. Since the first T final, it is plus minus half, and the second is plus minus half, so this is a 1 as a plus minus. The third step now is to find the percentage uncertainty. So we're going to take the absolute uncertainty now, which is 1, divided over the value, which is a 20, times 100%, and the final answer, it will be a 5%. Now we're going through question number 5, which is the last question of practice. Molly carried out an experiment to measure the enthalpy change of a solution of a salt. In order to calculate the final value, the following calculations was carried out. So I have here the rule. All the values are given. So let's read what we have. She took 50 plus minus 1 times 4.2, and it is multiplied by 20, and I have the plus minus uncertainty for it, over 1000 multiplied by 0.1 plus minus 0.01. Quantities without uncertainties can be assumed to be exact, such as the 4.2 and the 1000. How should the final value be quoted? So the first thing I'm going to find is the value. What is this value, which is the enthalpy value actually? Since she calculated the enthalpy values as given. Enthalpy value, it is so important for chapter number 5. Actually, you will be familiar on the word of enthalpy. So I'm going to take the 50. It is multiplied 4.2 multiplied 20 over 1000, and it is multiplied by 0.10. Now think about your final answer. Your final answer should be correct to how many significant figures? It should be 2 significant figures. Since here you have a 3, here you have a 2, and here you have a 3, and here you have a 2. For the 1000, don't take it into consideration, since this 1000 is taken for the converting part, and it is actually a let's say it's a number, so it's not important to take it into consideration for your final significant figures number. So it is 42 as a final answer. If I'm going to look for a unit, it's not so important now since you don't know the enthalpy, but if you do, it is kilojoule per mole actually. So the enthalpy, it is 42 kilojoule per mole. Now you're going to continue. The question is asking to code the number. So any number should be with a plus minus uncertainty. So I'm going to find the percentage uncertainty of the enthalpy. In order to take the percentage uncertainty, I'm going to take the percentages of all the numbers which will be presented, which are presented, and there is an absolute which is plus minus for each. So I have actually 3 numbers. So I'm going now to take the percentage uncertainty of enthalpy. I need to add the percentages of each variable. So it will be a 1 divided over 50 multiply times 100%. I'm going now to take the second, which is 1 divided over 20 times 100% plus the last number, which is 0.01 divided over 0.1 multiply times 100%. Now for the other numbers, which are 4.2 and 1000, as mentioned in the question, assume that they are exact, so there is no uncertainty for them. So I took all the percentages and add them together. Now using the calculator, the final answer is 17%. Now I have the last step, which is calculating the absolute uncertainty, which is the plus minus uncertainty for my enthalpy. So I will take the percentage, which is 17 over 100. Then I'm going to multiply by my value, which is the 42. So your final answer is plus minus 7.14, and since your final answer is without any decimal, so we're going to write it as plus minus 7. So if I want to quote my final answer, the enthalpy value will be it is 42 plus minus 7, and you're going to put the unit between brackets for both, so it is kilojoule per mole. These are some questions taken from paper 2 as a practice for section 11.1. Thank you for watching.